Hello guys, welcome back. Today, as I promised, I'm going to start our foundation course, how to create a foundation. This course is for civil engineering students. I think you learn it in semester 7 or 8. Okay, it's not important now. But if you have this lesson in your college or university, you can use this as a helping thing to learn more. That's a note that I read it for this course. Okay, let's start it. At the first, I say that this note can't make you a foundation designer. We are going after this theoretical course. We are going to learn SAFE to know how to create a foundation for our structures. But now we need to know a little theory, but I recommended you to learn this from your college or university. Okay, let's go. Bearing capacity of shallow foundations. We have many kind of foundation, but we have type of surface footing. Surface footing are spread footings. Spread footing. In spread footings, we have simple footings that carry the load of a single column. There are pictures of them. You can see here. I show them to you. We have a stepped footings that has multiple steps to distribute the load more effectively, and a sloped footings designed with a slope to spread the load over a wider area, and circular footing round in shape and distribute the load uniformly in all directions. Okay, as we can see, we have a sloping footings, circular, stepped, and simple. They are really easy to understand and don't need me to give you any more description. But also we have spread footings and combined footings. Combined footings are rectangular. Combined footings carries the load of two adjunct columns. T-shaped combined footings carry the load of two adjunct columns. They are the pictures. As you can see, we have the rectangular column here. In one we have rectangular, and here we have T-shaped. You can see the differences and the views. This view is from front and this view is from top. These are columns, as you can see. Okay, let's go. We have also a strip or continuous footing. A strip or continuous footing placed under a wall or under columns that are aligned on a single axis. The strip or continuous footing are the columns that one dimension is smaller than another dimension. As you can see here, we have load-bearing wall and a linear load and soil reactions. These are the reactions, and you can see the picture of them. Okay, we have raft or mat footing that we use the most, I think. In the pictures, you see there is nothing about them I want to tell you. It's easily to understand. They are footings that gain all the places. Okay, type of shallow foundation. We have type of shallow foundation. We can select the type of shallow foundation depend on this material. I will tell you more about in the next lessons. But now you need to know amount of column loads. This give to us by SAP or ETABS. We analyze them in these two software. Soil resistance by site analyzing. Inside we do some kind of experiment and get this. We speak about them later. Type of structures, that's also give to us. Other specific conditions, we speak about them later. Okay, bearing capacity of shallow foundation. The maximum stress that a shallow foundation can apply to soil is called the bearing capacity of the foundation. A shallow foundation performs correctly when the stress created under it meets the following two conditions: no shear failure, no excessive settlement. These are two important things that we need to cover them. Independent. The shear failure is the soil under the foundation should not fail in shear. If you don't know shear, this is something come from your past course in civil engineering. If you don't know that, this course is not for you. You must go and learn something easier. Okay. General shear failure. We have type of shear failure in soil. The first one is general shear failure. Consider a strip foundation on dense and or stiff clay soil. If a load is gradually applied to the foundation, the settlement of the foundation increased at a specific point when the pressure under the foundation reaches QU, which is the ultimate bearing capacity. At this point, the shear failure occurs beneath the foundation and the ground surface continues until the pressure is reached, which is called the ultimate bearing capacity of the foundation. The most important thing in general shear failure is that it appears on dense sand and stiff clay soil. Surface of repetition soil. As you can see, when the load is applied here, this shear fail happen here, and then the soil around the structure come up and the failure happen. As you can see, when we are applying the load it's the ultimate, and after that when we apply the load, only the settlement rise and no more load can have the structure. Okay, it occurs, it's very dense soil, dense sand or hard clay, where the soil on both sides has risen, but ultimately the surface slip and rotate in one side. It says that when the soil crash, the structure is rotated. The structure rotated like this. Let me delete this and create a picture for you. The structure is happen something like this. Okay, let's go and see what we have. Type of shear failure on soil. We have general shear failure that we tell you about. It's in the details here. We have local shear failure occur in sandy soils with medium density and the clay with medium stiffness. That's important to know what kind of failure happened in one kind of soil. No rotation in the foundation, the amount of soil uplift on both sides is less. That's the kind of failure happen. Gradual increase in pressure and a slight settlement. Okay, punching shear failure. This is really important in our designing, and you must need it. It occur in relatively loose soil. Notable settlement is observed. The foundation punches through the soil. It's like that. Let me create a picture for you. This is, for example, our soil, and we have our foundation here. The punch foundation is how when we apply the load, let me say Q, the foundation is go here. The foundation is go down. This is the punch failure. Load bearing theories of shallow foundation. We have some theories for determining the shallow foundation's load bearing. The first one is we are going to learn is theory of bearing capacity by Terzaghi. Terzaghi, with the following assumption, derived a relation for determining the bearing capacity referred to the figure. As I said, these are theoretical. You need them in the university, but I tell you a little about them to can create a good foundation in our safe software. Okay. Assumption. Shear failure occurs entirely within the shallow foundation. The soil above the foundation level or the ground surface is replaced with a uniform load equal to, this is important, equal to, okay. The triangular region immediately below the foundation forms. The contrast between the foundation and the soil below is smooth. Okay, we can see them in the picture that the Terzaghi says that the shear foundation here appear here. This is the picture. For more detail, if you want, you can learn them. I give you these notes. If you want, I give you these notes. Okay, let's see what the Terzaghi equation says. This is the Terzaghi equation. The QU is equal to CNC plus QNQ plus lambda B and a lambda. Okay, we can. The first term in the Evo relation is the term of cohesion. It's important. It's the term of cohesion, and the second term in do is the surcharge of in depth, and the third term the specific weight of the soil. Okay, this is a specific weight of soil, and this is the depth. That's important for you know. The bearing capacity factors NC, NQ, and lambda are dimensionless and depend only on the internal fraction angle of the soil. Okay, this is the equation for NQ, NC, and N lambda. And KPY is soil pressure coefficient, but we don't use them because we have the let me show you that we have this kind of tables that give us NC, NQ, and lambda for the thetas. We can see all of them are here. Okay, let's see angle. Equation or ultimate bearing capacity. If the foundation is square, the equation is what is here. If the foundation is circular, the equation is here. But this equation is for this kind of, let me show you the picture, is for the continuous footing. It's for the continuous footing. Okay, let's go and the things that changed, I light them a little for you to understand. C is the cohesion of the soil, Q is the surcharge load at the foundation level, lambda is the unit weight of the soil, B is the width of the foundation, and as you can see, NC, NQ, and lambda are bearing capacity factors depending on the internal fractions. Okay, if the shear failure under the foundation is local shear failure, use the following relations. If the shear failure under the foundation is the local shear failure, we have three kind of failure. If it's the first one, we use the equation up, and if the second one, we use the equation down. And you can see the terms are really similar, but some of the numbers are different, and I print them for you to understand. But the most important thing you must know is you use this theta instead of the theta we have. And the important thing I forgotten to tell you is that it's in radian. We use it as term of radian. The radian is that, for the one who don't know, radian is that P2, P3, I make a mistake, 2P, this is the radian. In the circle of radian, we use them. Okay, and for that, we have the table I told you about. And here, effect of groundwater on bearing capacity. Groundwater is also change the bearing capacity. We have the relation for a situation where the groundwater level is at a significant depth below to shallow foundation level as follows. The cases are conditional potential location of groundwater. If the groundwater is below the foundation level in such a way that the value of D1 is like that, we can estimate that, and you can solve it, but you just read it. It says that if the D is here, if the the groundwater level is different, we have these equations. That's not important because you can use them whenever you want, and we solve a problem from it. After Terzaghi, we have Meyerhof of bearing capacity equation. It has some assumption, the context of the soil with the foundation in the horizontal. The failure source of the soil is the logarithm scalar type. The shear strength of the soil above the foundation level is neglected. In the passive wedge, alpha is equal to 45 plus that. As you can see, the equation is really similar to the Terzaghi equation, but it has a little differences. We have diff factors, shaped factors, inequalization factors, and soil mechanics factors that have the equations we come you here, shape factor equations, and passive earth pressure coefficient. These equations, we use them in the problems that we solve for you to exercise that we solve for you to learn better. But they are the terms and we have them, but from the past we use NEQ, NSC, and Lambda as the table for using and solving them. Okay, this is the first lesson. No, we have another thing to say. We have DSC and D and I. There are two kind of the there are two kind of factors that we use them, that we find them from the theta. Theta is the load angle. The theta is the load angle that happened to us, and we can find them by finding the theta, and after that using this equation. If you don't understand anything, don't be nervous. We solve some exercise from them and then you understand them fully. Have a good day and don't forget to like and subscribe.